some other demos when we come back to it. Because there are many things you can do with a laser and a bunch of slits. Let's see. First of all, I need that meter stick. Oh, there it is. Good. Okay. So the distance here, I want to make it about 2.5 meters. So this is roughly 1 meter. That is basically 2. So I want it to be, let's say I get half. So that's 1 meter. This distance I'm getting it to about 2 meters now. And then I want 50 centimeters. Okay, so this is about 2.5 meters. Distance slit. Distance slit to distance slit to screen is about 2.5 meters. So what we've got is a slit that's 0.02 millimeters, and a millimeter is 1,000th of a meter, so it's 10 to the minus 3. 0.02 means we have 2 times 10 to the minus 5 meters. I had 10 to the minus 8 on Tuesday because I just took a millimeter of 10 to the minus 6 instead of obviously 10 to the minus 3. So that's the width of this slit. Then the laser light comes through, and the photons are approaching the slit with a certain momentum, which I'll write down in a minute. In fact, I might as well. I brought some notes here. Okay, hold. Yeah. So the momentum of each photon is about 1.05 times 10 to the minus 27 kilogram meters per second. So that's mass times velocity. That's mass times speed. That's momentum. On the other hand, we have a distance here, and well, I don't have that quite centered. The beam spreads out a little bit to something that I think is about 5 centimeters in total width. Well, we can say roughly 5 centimeters. Depends on how you count. And the reason this is a little bit tricky to estimate is that the intensity looks like that. That is to say, the more of the photons go to the center here than off to the side. And then there are some that get really scattered some distance away. And so it's hard to say what this width is, but basically the uncertainty in the position, the width is 0.02 millimeters, so the distance from the center is 0.01. So what I should really call delta x is approximately 0.01 millimeters, which is just 10 to the minus 5 meters. On the other hand, delta p is p times basically this angle here, and the angle is something like half the width, so that's 0.025 meters, right? 5 centimeters would be 0.05 meters, and we're dividing by 2.5 meters. And so the ratio of these two is a factor of 100. So this is 10 to the minus 2 times P. P, on the other hand, is essentially 10 to the minus 27, and so this is 10 to the minus 29 kilograms meters per second. Okay. And so what we do, the uncertainty relation is basically h over 4 pi is less than, more or less equal to delta x, delta t. So that's the Heisenberg uncertainty relation, or Heisenberg uncertainty principle. And so that gives us h as 4 pi 10 to the minus 5 for delta x, 10 to the minus 29. So that's altogether 4 pi 10 to the minus 34. And I think I wanted to divide, I think I should divide it again by a factor of 2 because, as I said, most of the photons are on in the center. So let me make that 2 pi. And so that's then roughly 6 10 to the minus 34. And the correct answer, in fact, is 6 times 10 to the minus 34. The correct answer is that h is equal to 6.626. Of course, this is the 4 figures, 10 to the minus 34, and it's kilogram meters squared per second. So you see, what I said we get last time was a factor of 10. In fact, we get something like 5% error or so, estimating it a little more carefully. There may be some questions there. Does anybody have a question?
I guess it's more of a math question, but
yes.
I'm wondering what you're doing when you're giving out Heisenberg's uncertainty. The original, thank you. The original h over 4 pi is lesser equal to delta x delta t.
This is what the Heisenberg uncertainty principle says, that if you're going to measure something, then the uncertainty in the position measurement times the uncertainty in the momentum measurement of the same thing at the same time, and these are both vector quantities, so we're talking about momentum in this direction, momentum along this axis here.
Right, right.
The product of those two has to be greater than Planck's constant divided by 4 pi.
Okay.
And so the deal is that if you do the thing carefully, it's more or less equal to Planck's constant over 4 pi.
Okay.
And in fact, it depends on the, I mean, when you apply Heisenberg's uncertainty principle in order to get in order to do a calculation, you sometimes get a good answer with the 4 pi, sometimes you get a good answer without the 4 pi.
Okay.
Depending on what other approximations are intrinsic to your argument.
Gotcha.
But roughly speaking, it's something that was discovered in around, I would say, 1925 or so.
Okay.
Planck's constant was invented by Planck back in, I think, 1890 or so, when he was studying black body radiation. In other words, how the intensity of radiation from an oven varied with the temperature of the oven, and how the intensity of the radiation varied with the frequency of the radiation. The oven emits in a very broad band of frequencies, and in fact, the curve is essentially an intensity wavelength, and it looks something like that. And what Planck was doing was explaining this part.
Okay.
Because this part over here was already known.
Okay.
Okay, well, I think later we'll do some more demos of this. But first of all, I think I should do some other things. There are no questions. Yeah.
How do you calculate
So what?
how do you calculate uncertainties like the x and
How do I calculate delta x and delta p? Well, it's a matter, in this case, it's a matter of estimating them. The slit is labeled as 1/50th of a millimeter wide. So that's, or 0.02 millimeters is how it's labeled. So that's the total width of the slit. So the uncertainty really in the position of the photon when it goes through is the distance the photon could be from the center. And that's only half the width, so that's 0.01. And now for delta P, well, first of all, this width is it was about 5 centimeters. So first you divide by 2 because you're really measuring from the center. And then secondly, I put in another factor of 2 because the intensity is falling off from the center. So you know most of the photons are going more or less straight through, nearly straight through. And then the idea was the photons were going in this direction, so when they come out of the laser, the momentum along this direction is 0. But by the time they get to the screen, you see they're not all in the center. So that means some of them are moving a little bit this way or a little bit that way. And the amount they're moving is roughly 1/4 of 5 centimeters divided by 2.5 centimeters. And so that's what I used. And what I did Tuesday was I took 0.02 millimeters and translated it into meters with an extra factor of 10 to the minus 3, which screwed everything up.
But it's essentially taking the other pieces of data that you can find and then just getting or plugging them into the right places, just like anything else. Like you took
Yeah, I'm just setting h over 4 pi equal to the product of these two. What we know is this has to be bigger, and the other thing we know is that the position measurement is really well done because that's a commercially manufactured slide for demonstrations of this kind. This is a commercial laser, and in other words, the measurements that I was doing were pretty good, and so, I mean, roughly so that we could. The experimental setup is one that apparently, because the calculation worked to 5% or so, is well suited for getting delta x times delta p as small as possible. You can't get any smaller than h over 4 pi. I was setting it equal to h over 4 pi, and the result of the calculation is that it is that to it. You can get it that small to within 5% or 10%. Okay. Now I want to do various demos. One demo is what is force? And force is, well, Newton's law for force is mass times acceleration. And acceleration, of course, is a vector, so is force. And relativistically, the formula is a little bit more complicated. This mass itself is the rate of change of the velocity, and the rate of change of something is, it's really the time derivative. Equivalently, it's, well, rate of change. And one often uses a dot to represent the rate of change of something. The relativistic expression is mv dot over the square root of 1 minus v squared over c squared. Let me make sure I've got that exactly right. Well, it's a little more complicated than that. It's that it's, let's put the m there, and then it is it's the time derivative of the momentum. And momentum is mass times velocity over square root of 1 minus v squared over c squared. So the relativistic expression is, well, I don't need the m if I have p dot. So it's the rate of change of momentum times this factor, and the momentum itself is mv over the square root of 1 minus v squared over c squared. Okay, but at low speeds, for ordinary situations, for most uses of the term force, we can use Newton's expression, which is just mass times acceleration. Now we can get an idea of what mass is with this lead brick, which is heavy. And so I'm going to do a demo here. I don't know if I've ever done this demo. It says that when you do the demo, you don't get injured. Since I've never done the demo, I'm not sure about this. I hope we're not talking about a factor of 1,000 like the one that I'm the other. Okay, so I'm going to whack this. And you see it didn't hurt my hand, whereas if I had whacked my hand with the hammer, big time hurt. Okay. But instead, this didn't hurt at all. What's the reason for that? The reason is that when the hammer hit the brick, the lead brick, it transferred some momentum to the lead brick. But if we look at the lead brick, the formula for momentum for slowly moving lead bricks is just the mass of the brick times the speed of the brick. The mass of the brick is huge. I could barely lift it. And so the speed that the brick got due to my hitting it with the hammer was very low. And so the pressure effectively of the brick on my hand was such that it didn't hurt. And so this lead brick is a really great illustration of what we mean by mass. Okay. It's hard to accelerate something that's really heavy. And we need to distinguish mass and weight. What's weight? The weight of something is the force the thing exerts on a scale. But the force the thing exerts on a scale, for example, the weight of this brick, the brick is pushing on the table. Now, why is the brick pushing on the table? It's pushing on the table because the gravitational field is pulling it down. And in fact, the deal is that the lower the brick gets, the lower the potential energy. The potential energy, which is negative, goes down. And the potential energy here is the potential energy of the Earth brick system. Let me write down what that is. Is minus G, one mass, the other mass, over the distance between them. That's the potential energy of a mass m that's a distance r from another mass m. And G is what's called Newton's constant. And the actual value of Newton's constant, which if you Google all of these things, it's 6.67 times 10 to the minus 11 meters cubed per kilogram second squared. The units that I'm trying to use most of the time in this course are the standard meter, kilogram, second units, which are basically the standard units of engineering and physics internationally. Sometimes, I mean, it doesn't matter what system of units you use, it's just that you can't use two systems of units at the same time. And I think, I'm told that one of the expensive space accidents, this was expensive in just dollars, not people. One of the robot rovers crashed into Mars, I think.
It was the weather observer, right?
A weather balloon?
Yeah, a Mars weather observer or a climate observer or something like that.
Going around Mars?
Yeah.
Okay, good. Here, you get a candy for that.
Sweet. Thank you.
Anyway, the reason for the crash is one group of engineers was using inches, feet, and seconds, and maybe even pounds. And the other group was using meters, kilograms, and seconds. And they weren't talking. They apparently lived 1,000 miles apart, and never realized that they were using two different systems of units. And the result was a satellite that crashed into Mars, which was a big embarrassment for the people there. We can get an idea of potential energy and kinetic energy and so forth in this demo. I've done various demos of this effect. And here, you see there are two balls here, metal balls, solid metal balls, and there are two tracks. They start out the same, but then one goes down and then back up, and one stays constant. And what we'll see is that they're moving at the same speed here, which means that the kinetic energy is conserved. Frankly, I don't think that's a very effective demo because we don't really know what the kinetic energy of these guys was. But in fact, all right, I'll do it one more time and you can see if they should go to the same distance. And I imagine they do, that you can kind of see that. I guess the trick is that the first ball to arrive moves the target. And so let's see, I can maybe put the candy in the water, and some chalk here maybe. Is that where they landed basically?
More or less, yeah. We'll see.
So I'll do it one more time. Well, approximately. Okay. Now, what I described energy in various ways. This is gravitational potential energy. You see, because of the minus sign, it's negative. You can imagine doing some work. Well, what is work? Is force times distance, and it in fact represents a change in energy. So if I lift this thing, I'm doing work on the brick Earth system, and I'm increasing R. The potential energy, therefore, which is negative, becomes a little less negative. And the amount that it became less negative was the force that I had to exert, which is the weight of the brick times the distance, which was about, I don't know, 30 centimeters or something. Now, what is that conversion factor that gets you from mass to weight? And it's the acceleration of gravity. So the weight of something is g, the acceleration of gravity, times the mass. And the acceleration of gravity, g, is something like 9.8 meters per second squared. Can you guys see that when I write on that board? Can you see it in the front? Okay. It's also, in English units, it's 32 feet per second squared.
So it was negative 9.8.
Huh?
So it was negative 9.8.
Well, negative depends upon whether, if you're counting, I was just writing the magnitude first, but the negative would be, because normally you think of this as the positive direction and the acceleration of gravity is down, you'd say minus. So minus 9.8 is certainly correct. But 9.8 is also, if I'll keep the minus sign in my head. All right, so you get a candy too. Good. All right, so let's see. Any other questions? So when you step on a scale, what you're measuring is your mass times the local acceleration of gravity. And here in Albuquerque, we're a little bit farther from the center of the Earth than people in, say, New York or Houston, but it's a very small effect. It's been part in 6,000 or something, 4,000.
So when the ball rolls,
Yeah,
and the second ball, I guess the one that actually has the dips in it,
yeah.
it's the potential energy of the ball is being exerted, or
Well, Jesus
oh.
Christ. The potential energy of the ball
well, it's being
was being,
Yes,
what's
yeah, it's
conserved
being
is the
converted.
total energy. The potential energy plus the kinetic energy.
Gotcha.
And
Gotcha.
the potential energy went down in the sense that that the height dropped by a few centimeters.
Mm-hmm.
And that was enough to move these things along at a reasonable speed.
Okay.
Now, if you ask, well, what was the total potential energy that was given to the balls?
Mm-hmm.
We can compute what it was because it's the mass of the ball. I'm not quite sure what that is. Times g,
Mm-hmm.
and times the extra height there above this height. And so that was about a 20th of a meter. And if we take g equal to 10, then this is m over 2. And so what does that mean? That means that at the other end, the speed they were going at, which was m over 2 v squared, that means that they were moving, that v squared had to be 1. So v was a meter per second here.
Okay.
And, okay, so that shows you how potential energy gets converted to kinetic energy. I could do it one more time and we'll see if they looked as though they were moving in meters per second. In fact, both should have been moving in a meter per second. Okay. Let's do a momentum, another momentum. All right, we've got a little problem here. I don't think I need the thing at 2.5 meters anymore. And now I haven't done this in 7 years. This is the last time I've taught this course in lecture form. And what we've got here are 2 cylinders of CO2, 4 bicycle wheels. We've got a lot of extra. I guess if there are 2 students who want to come with me, we've got enough earmuffs for 2 students. And apparently, I think this is overkill, but these are gloves in case this gets too cold. I don't think that's really going to happen.
Yeah.
All right, so let me just move this out of the way a bit over here.
Go for it.
All right, well,
I would, but I'm on camera, so.
all right, there's something wrong here. I could try the other one, but yeah, see this one works, but this one doesn't. And all right, well, I'll just here I'm doing work and giving it kinetic energy. I'm pressing a force times the distance is work done. And now I'll just use whatever's left in that let's see what happens. This is the second demo that has not worked because the guy in the back there doesn't bother to get the demo. That's too bad because that's one of our better demos. But obviously somebody has to fill the cylinders with carbon dioxide gas at high pressure, otherwise it doesn't work.
So, like, if that were to work,
If it had worked, we would have had carbon dioxide gas going out of one of the cylinders in that direction, and that would have been, momentum would have been, the carbon dioxide gas would have had quite a bit of momentum in that direction.
okay.
But by conservation of momentum, the cart would have acquired the same momentum in the opposite direction, and I would have gone sailing across the room.
Okay. And then the pressure of the gas along with the momentum would have been...
Well, let's think really just in terms of conservation of momentum. At first, when I'm standing there, before I pull the trigger, momentum 0.
Right.
I pull the trigger, we get big momentum of carbon dioxide that way. Therefore, the momentum has to stay 0, and so we got to have a lot of momentum of the cart going this way.
Okay, so they cancel each other out.
They add up to 0.
Okay,
Yes,
gotcha.
They cancel each other out.
I'm going to take all the candy from everybody if I keep it.
Well, I'll just go to Costco. Costco, by the way, I think is one of the best corporations in the world. They also pay their employees pretty well. In fact, I remember reading an article in the Wall Street Journal. It was column 1, page 1, about 15 years ago. And the column said, certain stores, most stores sell things at high prices. Walmart sells things at pretty low prices, but pays the workers almost nothing. Costco sells things at really low prices and pays the workers well. How are they going to make ends meet? That was the Wall Street Journal article. And evidently, they've been a success. And I, in fact, once met a man on a plane who was in the importing shoes. And I said, oh, do you sell them to Costco? And he looked at me and he said, I don't know how anybody can make any money selling anything to Costco. Which is, Costco drives the price down so much so as to be able to pay the workers and give the customers bargains. Okay, well, that's not exactly physics, but it's kind of economics. Okay, now here is another demo of force and mass and so forth. This is the kind of nice demo. Okay, now. All right. So what I want you to do is to imagine what's going to happen. I'm going to do this demo in 2 ways because we've got extra thread. One way, I'm going to pull this down really fast, and one of the threads is going to break. The second time, I'm going to pull very slowly, and one of the threads is going to break. Okay. So think and guess. All right. The first thing, I'm going to pull really fast. Now, the lower string broke, but not the upper one. Now, why was that? The reason is the same reason that my hand didn't get crushed when I whacked the lead brick. Namely, the force that got applied to this heavy weight transferred some momentum to the heavy weight, but the heavy weight being heavy hardly moved. So this string didn't break. Now I'm going to put another one here. And I'm going to pull slowly. And if I pull very slowly, this one should break, and not this one, because the stress on this one will be my force plus the mass of this sphere times the acceleration of gravity, or the weight of the sphere. So you'll have two forces on this thing. So I'm going to pull slowly, and I'm going to hold my hands out so I don't, because that big ball's going to fall, probably fall on my toes. Okay, so you see the upper one broke, and that was it. So this is an example of mass and force and acceleration. Okay. Want to see it again? Yes.
Might as well, yeah, I'm up for it, yeah.
Huh?
I'm up for it, yeah.
Sure.
I would say I'm up for it, sure.
Oh, okay. All right, let me see how many pieces.
Yeah,
of
if you
this-
can, yeah.
Yeah, I've got enough to do it one more time, but only one more time. Oh, it's tricky. It's tricky.
So is there a, like a sweet spot that you have to find as far as how quickly or how slow, or is it really not matter, I mean, for the most part?
Well, you're right. I mean, the first time I pulled really fast, and the second time I pulled really slowly. And that was to make sure that one or the other happened.
Right.
And obviously, if you go in between, they might break simultaneously.
Okay.
All right, what do you want, fast or slow?
Yeah, I'm up there, might as well.
I don't know what's in between, though.
Well, slowly is a bit more interesting. It's more in,
I like
A little louder, what? The one I think is more interesting is the fast, because it illustrates the that the mass here had almost no effect on this upper string. Okay. Actually, you don't want to do your momentum demo again. All right, so since the jet car didn't work, but this guy is still quite able, beyond his strong and so forth.
really.
All right, now, what I want you to do is, before you go up and, don't go anything fancy until you get to the other end. Just go in a straight line and, one push and then there. Now, he has a certain mass. Once he gets started, he's going to move at a certain velocity, and what you'll notice, because it's a good skateboard, is that he should be moving at the same speed at the other end of the room. And, okay, so do it. Good push. So his speed is conserved. Obviously, it's the same man, so his mass is conserved. And for the non-relativistic momentum, it's just the mass times the speed. And so you saw here conservation of momentum. Great. All right, you go any way you want. Well, my demo is here.
they're good.
Yeah, so you said that.
You know, every time I study to try to like have lulls
I'm sorry, say it
myself
again?
with
For the
physics,
white
every time I need to
the
physics.
CO2, if it were to work, which one would be positive and negative? Because you said that they had to equal 0.
Well, okay. How you assign the signs, I mean, it's sort of up to you. But you do you turn on the gas, okay? and then you've got momentum going in that direction. So it's positive in that direction, negative in this direction. And to make to have the momentum still zero, you've got to have the cart have an equal momentum in this direction and the gas an equal momentum in the other direction. So that's the way I think of it. If you want to think in terms of positive and negative, well, let's make the cart going this way positive, and then the momentum of the gas molecules is negative in this direction. And you add the two together, you get zero. But you can also think of them both as positive, just pointing in different directions, and you add vectors that are pointing in opposite directions. If they're of equal magnitude, then they add up to zero. So that's another way of thinking of it. All right, let me say a few things about this diagram here, and let me maybe turn off some of these lights to get a little more so that we get so that we can read the screen there. This is on the website, so you don't need to copy it down. You can just go to the class website, which is it's quantum.phys.unm.edu. And then slash, and the slash is 102-17L, lowercase l. And what you can see there are various lecture videos of links to YouTube versions of the lectures, and including the one where I made an arithmetic error of 1,000. All right, so this is a quick review of what we've been saying about cosmology. The universe is 13.8 billion years old, at least the known universe. It started with, as I said to you, the best theory of the start of the universe is inflation, and what started inflation isn't really known. It could be some quantum fluctuation. Then after about 4 minutes, the temperature dropped below 1 billion degrees, and one had protons, neutrons, and helium nuclei. By weight, it was 3/4 hydrogen, 1/4 helium, but since helium is 4 times heavier, there was only 1 out of 16 particles then would have been helium. The energy of the plasma was mainly radiation. For about 51,000 years, it was radiation mainly. Then, as the universe continued to expand, remember the violent expansion is only during inflation, and that's a very small fraction of a second. After that, the universe, the scale factor of the universe, or if you want, the universe is expanding like the square root of the time. Then after 51,000 years, most of the energy is matter, and the expansion actually accelerates, and it goes as the 2/3 power of time. And then, let's see what the actual number was. About 3.6 billion years ago, the dark energy started to accelerate the expansion of the universe. And I'll give you some graphs of this later. Now let's see, how do I get to the next form? Okay. So here's the conversion factor to go from electron volts to degrees Kelvin. It's a factor of 10 to the 4th, basically, but the temperature during the first, yes.
Are these going to be online as well?
Yeah,
This
all this is
PowerPoint?
online, yeah, there's a lot of stuff online.
Oh, I don't.
No, that's okay. Oh, all right, give it to somebody else. So, early on, the temperature was something like 10 to the 10th Kelvin. And so that's really, really hot. Hotter than the temperature of the center of the sun might be 10 to the 7th Kelvin. This is 1,000 times hotter. Of course, when I say 1,000, you people are not going to trust me. But it falls off as the square root of time. And the scale factor, that's called A. It increases like that. That's the expansion of the universe. Okay. All right, let me skip some of these formulas here because I think, all right, that's one of the things I wanted to get to. This is one of the reasons why people are pretty convinced that dark matter exists and is important. This, I'll try to darken the room a little bit. So this is a very nice picture of the bullet cluster. And what you're seeing there in false colors, the astronomers love false colors. They're geniuses at false color. But it plays a very useful role here. The red stuff is matter. It's the matter of two galaxies that collided. The blue stuff is more matter. And in fact, it's most of the matter of the two galaxies. And what you see here is that the blue stuff on the left, the two things on the blue stuff on the left is matter from the galaxy that was moving this way. And so it went right through the collision. The blue stuff on the right is matter that went through the collision and is still moving up in that direction. And what we're learning here is that that blue stuff can go right through the matter of a galaxy unimpeded, whereas the red stuff gets stuck. And the interpretation is, and I think the measurements of the light from the red matter, those measurements from there indicate that that is actual gas. It is the matter that we know about, namely hydrogen, helium, and so forth. So you might say, well, if the blue stuff so the blue stuff is interpreted as dark matter. But then you'd say, well, how do we know even if it's there if we can't see it because it's dark? And the reason we know that the blue stuff is there is because we can see in the pattern of the galaxies around this collision, we can see that the form of those galaxies has been distorted by what's called gravitational lensing. And here's an example of that. What you see here is in the center here is some enormous mass, and it could be dark matter, or it could be massive black holes, it could be anything that's just extraordinarily massive here. And then there's light from very distant stars and galaxies coming from behind this mass. And that light gets bent around, and the result is these streaks that are, as you see, they're curved, and they're all sort of consistently curved so that they kind of make a circle like that. And in particular over here as well. And that's gravitational lensing. Let me turn the light's on so I can illustrate this a little better. In fact, maybe I could just put this light on. Yeah, I've got some blackboard over there that's unused. So the idea is that you have some huge mass here, and you have light that comes from some star here, or galaxy, or quasar, something extraordinarily bright. And what happens? Well, what happens is the light that goes this way goes right through the mass, and it either gets stopped by the mass or it keeps going. And that light doesn't really enter into the gravitational lensing. On the other hand, the light that comes up this way ordinarily would continue to go that way if the mass weren't there. But the mass then attracts that light and makes it go back down like this. And similarly, the light that was going down this way and that ordinarily would keep going in a straight line gets bent by the mass and comes across like that. And so if we're actually looking instead directly at the mass, then what we're seeing for a given very bright point source, we might see if it's directly behind the mass, we might see it as a circle of light. And by knowing what the geometry is here, how much the light is bent, we can figure out how massive that object is. This was something that was suggested first by Einstein a very long time ago, and for a while it wasn't measured, but now these days it's used to make measurements, and in fact that's how we know how much mass is here and how much mass is here. And in this bullet cluster, I guess this looks like a bullet, in this bullet cluster, the ordinary matter is left behind because it's scattered and interacted with itself. The two galaxies interacted. Each galaxy slowed the other one down, like two huge clouds of gas. On the other hand, the dark matter just sailed through. So there's a photo of a younger Einstein. Basically, well, I don't know if we want to go into that. Let me just, I think, just get to this picture. Here's a picture, a graph of the scale factor on the left. The y-axis is the scale factor. And this is the time in 1,000 years, kiloyears. And the red curve is the scale factor, so how much the universe is expanding. And initially, for the first 51,000 years, when radiation is dominant, it's expanding at the square root of time. And then up here, it's not quite linear. It's going as the 2/3 power of the time. And what I've plotted here are the radiation densities with the numbers on the y-axis on the right-hand side, kilograms per meter cubed. And the units here are, of course, 10 to the minus 16, because space is mostly empty. And here's the matter density falling fast initially, whereas, and the radiation density, both of them falling fast, but the radiation density is falling faster. And they cross at about 51,000 years and then continue like this. So for the first 100,000 years, you could say that in a certain sense, matter and energy were comparable in the energy densities. But before, for the first 51,000, mostly radiation. And after that, it was mostly matter. The reason why it's radiation at first and then matter is that the radiation, well, in the beginning, all you had was radiation, because all the particles were moving relativistically, and so it was, the masses of the particles were a very small fraction of the energy. It was all the energy of motion. In other words, it was mc squared over root 1 minus v squared over c squared. It's that 1 over 1 minus v squared over c squared that was all of the energy, because 1 minus v squared over c squared was essentially 0. And so it was mc squared over 0. And so there was an enormous amount of energy. It was all radiation. But as the thing cooled off and as the scale factor expanded, the wavelengths expanded, and so consequently the momentum of the photons went down, and whereas the energy density, once the temperature dropped so that most of the energy was the masses of the particles, then the energy density just goes down as the cube of the scale factor, because there are just so many protons, so many helium nuclei. Both are stable, and the energy density is just how many of them per cubic meter. Of course, I'm leaving out the dark matter, which I almost always do, and most people almost always do, because we don't know what it is. And but in the calculation of these curves, I included the dark matter. So these curves are accurate, and this matter then is the total matter, dark plus light. So I'll skip that. Here is I think, a better picture of the CMB than the one that I was showing earlier. The reason is that this is from the Planck satellite that the Europeans put up, I don't know, 5 years ago or so, maybe 7 years ago. And at about 380,000 years after the Big Bang, the temperature dropped below, the temperature was dropping below 3,000 Kelvin, and at that temperature, below that temperature, hydrogen atoms and helium atoms are both stable, and so the universe suddenly became transparent, and the light that we're seeing now is coming from all directions. I should let me draw a quick diagram of that I should have drawn earlier when I first explained it. There's almost no unused blackboard, but let us say here we are. That's us, okay? We look out, and then I'm going to draw a two-dimensional picture of the universe. Okay, the CMB, so us is really here, and this picture of the CMB is coming from all directions. And as I've said to you many times, after you subtract out the Doppler shift due to the motion of the Earth, which is mainly the motion of the Sun and the galaxy, after you subtract that out, then this light is coming towards us from every direction, and with equal intensity to within 1 part in 100,000. You might wonder, why is it squashed like that? Well, from top to bottom is basically north to south. That's 180 degrees. But this one is, say, from New York, or the view from New York, looking out, then from, let us say, Omaha, then from San Francisco, then from Hawaii, then from Japan, and then from, I don't know, Moscow or something, Paris, and then back to New York. So in other words, it's 360 degrees this way, 180 degrees that way, and that's why it looks like that. Any questions? Yeah. All right, hold on, I gotta get more candy.
So is it supposed to be like like the inside of the sphere.
Sorry.
It's fine. The inside of the sphere, like us in the middle.
Yeah, we're in the middle, and and the light that is now hitting us
Yeah.
left has been traveling for 13.8 billion years.
Right.
And it's coming at us from all directions. And in fact, you know, if I had a three-dimensional blackboard, I would have made this thing a sphere, and we're at the center. And the radius of the sphere is 13.8 billion light years. All right, let's see what else we've got here. This is a plot. This is one of the most confusing plots in science. Here we've got, what we're plotting here is the temperature fluctuations in fact, correlations of temperature fluctuations in millions, in squared millionths of a degree Kelvin, and angular size. So what you're seeing is that there are huge fluctuations on an angular scale of about 1 degree. And now, if we go back to this thing, that's kind of what we see. If you look at that, you see that if it's 108 degrees north to south and 360 degrees east to, it's not really east to west, it's east to east because it's the whole circle, you can see that the fluctuations are around a 1 degree size, roughly. And that's what is shown here. The red curve is theory, and the theory is actually kind of complicated, but there's a simple aspect to it. This big bump there, that bump is, the idea is that during inflation and during the first 380,000 years of expansion, some of the quantum fluctuations that were just quantum fluctuations during the era of inflation and during the very early universe, then began to expand. And they could expand at what's called the speed of sound in that plasma, which is less than the speed of light by a factor of, wow, what was that? Andy, square root of 3. And so how much of this, how big could those spots be? Well, it's 380,000 years times the speed of light divided by the square root of 3. That's the size of those sort of spots. And it turns out that if we view them now from planet Earth, they're about 1 degree in size. Here's a plot of the first 50 billion years, and of course, we are there, 13.8 billion years. What you see on this scale is that the initial part here, where the era of radiation, which is only 51,000 years, is almost insignificant. And then the era of matter goes out to here. And then ever since that, you have an exponential expansion. We've only seen the first 3.6 billion years of that exponential expansion. But if we project out to the future, you see that there's going to be an enormous expansion of the energy density. And on this scale, the radiation density is negligible. This is the total matter density, dark and ordinary matter. And this here is the known value of the dark energy density. Of course, as I said to you before, many times we don't know what dark energy is. The leading theory is that it's some kind of energy that's mostly time independent, a kind of potential energy. But depending on what the theory is, the thing that accelerates the expansion of the universe is whatever the theory gives it, and whatever the equations of general relativity give. And it's essentially, in fancy language, it's the time component of the energy momentum tensor. So I guess it's the energy component of the energy momentum tensor. Let's see if there's anything else here. I think I may have run out of, oh, no, that's a nice picture. So this is a picture of this picture is a little older. And when this picture was made, they thought the universe was 13.7 billion years old. But they got the 380,000 right. So here, quantum fluctuations, inflation. Now, of course, inflation was much shorter than what we see on this picture. And there is the CMB. And then there was something like 400 million years before the first star formed. And the first stars, of course, formed presumably by collapsing clouds of hydrogen. And until the cloud collapsed enough to get hot. And how is this happening? Well, when you collapse, the negative gravitational potential energy goes way, way down, and to keep the energy constant, the thermal energy goes up, and the cloud gets very hot. So after 400 million years, we had stars, and then the rest of this is hardcore astronomy, so I'm going to skip it for now at least. Here's another picture that's more recent, and they got the age of the universe, more accurately, it's 13.8 billion years. And this is a nice picture because they've got the times more explicit. So a very small fraction of a second inflation. It wasn't until a millionth of a second before protons were stable. After 100th of a second, protons could form helium, protons and neutrons. After 3 minutes, you had formed already the hydrogen and helium and some of the light elements. 380,000 years transparency, and then the modern universe. Okay. I think we're at the end of the hour within a few seconds, so let me turn the lights on. I don't want people